Welcome to this course on fluid mechanics. In module 1, we will talk about fluid properties, a bit on Pascal's law, manometry. And so today we will start with fluid properties. So what is this subject or course on fluid mechanics? So it's a branch of science that deals with the behavior of liquids or gases. So liquids and gases together, we call them as fluids. Okay. To be a gas. So we are studying about the behavior of this liquid or gas at rest or as well as in motion. Okay. So we can subdivide the subject as fluid statics, fluid kinematics. So whenever we deal with fluids at rest, then we call it as fluid statics. Whenever we deal with fluids that are in motion, but I'm not going to consider the effect of the pressure forces, then it is called as fluid kinematics. Whenever I study the fluid that is in motion, and in addition to that, if I consider the pressure forces which is involved in the flow, then that is called as fluid dynamics. So all these three coupled together, fluid statics, kinematics, and fluid dynamics, we call that as fluid mechanics. Okay. So with that introduction, let's move on to the fluid properties. Some of them are very basic, but let's have a look at it. One of the basic property is going to be density. We all know that density is going to be mass by volume. So this density can also be, or it will also be referred to as mass density. So we can call that as mass divided by volume. So M divided by V, the unit is going to be kilogram per meter cube. The second property that we will look at is specific weight, and it is also called as weight density. It is the ratio of the weight of the fluid to its volume. So it is basically denoted by small w. Okay. And this is defined as weight of the fluid. So weight, it is basically defined as mass into acceleration due to gravity. So m times g divided by volume. So this mass by volume can be called as density rho, and that is what is written as rho over here. So it is rho times g. So yeah, specific. And if you look at this, so mass times acceleration due to gravity, that is similar to F is equal to ma. So force, the unit for force is going to be Newton, and the unit of volume is meter cube. So it is Newton per meter cube. So specific weight denoted, or it is represented in terms of Newton per meter cube, and it is denoted by the symbol W, small w. Then we have specific volume. Specific volume is denoted by small v. It is nothing but volume divided by mass. So volume divided by mass is your specific volume, and it can be written as 1 divided by mass by volume. So if this volume term v is taken to the denominator, so that becomes m by v in the denominator, and mass by volume is density. So your small v is going to be 1 by rho. Or the other way around, we can also say that rho is also going to be equal to 1 by small v. So specific volume, the unit for it is meter cube per kilogram. And the inverse of it is going to be kilogram per meter cube, which is nothing but your density. Okay. One more property, basic property, which we'll look at is specific gravity, and it is also called as relative density. So this is going to be a ratio, the ratio of the weight density of the fluid, which is nothing but your density, the density of the fluid, the given fluid, or the fluid for whom we are going to find the specific gravity. Okay. So the ratio of the weight density of the fluid to the density of the standard fluid. So what is going to be the standard fluid? So if it is going to be a liquid, it's going to be water. And if it is going to be gas, the standard fluid is taken as air. So the density of water is 1000 kilogram per meter cube, and approximately the like 1.03, 1.06. So depending upon the temperature, this density value slightly changes, but is always around 1. Okay, so the specific gravity is denoted by the letter capital S. So S is equal to density of the liquid divided by density of water. So it is rho of the found divided by 1,000 because density of water is 1,000. So in this case, it is going to be rho of gas divided by 1, which happens to be the density of air. Okay, so we have looked at four basic properties. One is your density. Density is mass by volume, weight by volume, and specific volume is volume divided by mass. And the last one which we have looked at is specific gravity, which is the ratio of density of the fluid divided by density of the standard fluid. Okay, so let's solve a very simple problem over here that is given to us. Calculate the specific weight, density, and specific gravity of 1 liter of the liquid, which weighs 7 newtons. So what is given to us is, so if you look at the given details, the volume is given as 1 liter. So capital V is 1 liter. And make a note that 1 liter is 10 to the power minus 3 meter cube, which is nothing but 0.001 meter cube. Okay, and they have said that it weighs 7 Newton, which means the weight of the liquid, which is mass times acceleration due to gravity. Mg is given as 7 Newton. And what is that they want us to find out? They want us to find out the specific weight W. They want us to find what is the density rho. And they want us to find what is the specific gravity for this specified liquid. Okay, so the first one is they want us to find specific weight. So specific weight, by definition, it is going to be weight divided by volume. That is times G divided by capital V. So M times G is given as 7 Newton and the volume is given as 0.001. So this is going to be 7 into 10 to the power 3. So that is 7,000 Newton per meter cube. Value, which we calculate. Then they have asked us to find the density or mass density. So density is given by rho. The usual definition is mass by volume, but here in this case, volume is known, but mass is not given to us directly. So what we can use is we can use the same definition which U is mg times v. And let me couple this mass by volume and write it as a rho times g. So from the definition of specific weight, I can write it is the specific weight divided by acceleration due to gravity. So it is 7,000 divided by 9.81. So let us use the calculator here. So it is 7,000 divided by 9.81, which is 713.56. And the unit is kilogram per meter cube. Okay. And then what else they want us to find is the next one is specific gravity. So the specific gravity of this fluid they want us to find. So specific gravity is given by capital S, which is density of the liquid divided by. So this is a water. So density of the liquid, we have just found that as 713.56 divided by 1,000. So it is going to be 0.71356, or approximately we can write this as 0.71. We have got the specific weight as 7,000. We have got this density as 713.56 kilogram per meter cube. And we have got the specific gravity as 0.71. Okay. So very simple example where we look at calculating these simple fluid properties. Okay. So the solution is given here. I think that is what we have got as well. Okay. And one more example is given. So they want us to calculate the specific weight again, which is W, the density, And now they want us to find the weight as well, mg, of 1 liter of petrol with specific gravity 0.7. So what is given here is they have given the volume as 1 liter, and we know that it is 10 to the power minus 3 meter cube. And the specific gravity of petrol is given, which is 0.7. Okay. So what we can find out is what we know is specific gravity of petrol can be defined as rho of petrol, and petrol is a liquid. So the standard fluid is supposed to be water. SP is given as 0.7, that is specific gravity of petrol is given as 0.7. Density of the petrol is what I am supposed to find out. Then density of water is 1000. So we get rho P is 0.7. That is 700 kilogram per meter cube. So we have estimated the density first. So what we can find out next is they want us to find specific weight. Specific weight is, we saw that in the previous problem. So it is 700 into 9.81. Okay. And so we use the calculator again. 7,000 into 9.81. So that is 6867. So 6867, the unit is Newton per meter cube. Okay. And then what else we are supposed to find out is weight. So W is mg divided by the volume. And the specific weight, we have just estimated that as 6867. So mg is what we are supposed to find out. The volume is 10 to the power minus 3. So mg is 6.867 newtons. This mg is nothing but your weight. Okay, so we have estimated the density as 700 kilogram per meter cube. The specific weight is 6867 Newton per meter cube, and the weight is 6.867 newtons. Okay. So that is what we have seen in our results as well. So our results are correct. Okay, we will move on to another important fluid property, which is called as viscosity. So viscosity, when you look at viscosity, look at this diagram over here. So what is shown here is the surface. So imagine that this is going to be a some fluid, say water. It flows through the pipe. And this is the upper wall of the pipe, and this is the lower wall of the pipe. And so you can see that there will be the first layer, that is the first layer of water that is touching this wall. And then you would higher and then layers of water till it reaches the upper plate. So on, you will have multiple layers over here. So what we know is, see, this fluid which enters with a particular velocity, people call it as free stream velocity. That is, so it is called as free stream velocity. And it is usually represented by the term u infinity, suffix infinity. So u infinity is the velocity with which fluid enters the pipe. So if it is going to be a circular pipe, later on we will look at this, but for the time being, you can take it as such. So this fluid, if you take that it is a circular pipe, the experimental results tells us that the maximum velocity or the free stream velocity can be seen at the center of the pipe. And if you look at the first layer of the fluid, see, this wall of the pipe is stationary. So the first layer of the fluid that is in contact with this wall, that is also stationary. So the velocity of the first layer of the fluid that is touching the walls of the pipe has got zero velocity. And people call that as no slip condition. A no slip condition is the condition when the plate is fixed or the wall of the pipe is fixed and the first layer of the fluid that is in contact with the stationary wall, the velocity of that particular layer is taken as zero. If so, then we call that as a no slip condition. First layer, the velocity is going to be zero. And somewhere at the center of the pipe, the velocity is going to be u infinity. Okay. So now let's consider two such layers. So there is one layer. Let me take this layer over here. Then let me take another layer which has got a velocity u plus d. Okay. So here I told you that at the wall of the pipe, the velocity is zero. And then at the center of the pipe, you are going to have the increase of the fluid as you move along the distance across the pipe. And that distance is taken as y. The walls of the pipe are separated by a distance y. So now by a distance dy apart, so let me consider this guy over here. This is the lower layer. And let me consider this guy on the top. Let me consider this guy as the upper layer, separated by a distance dy. Okay, the lower layer has got a velocity u, and the upper layer has got a velocity u plus d. Okay, so what is the difference in the velocity between these two? That is the final velocity minus initial velocity. So u plus du minus u, that will give you du. Okay, so within this differential space dy, I have got a difference in velocity du. So this du by dy is what people call as the velocity gradient. That is the change in the velocity as I travel along the distance y. And so it is called as velocity gradient. Okay. And now why it is important to us is, see, there is a change in velocity as I move along the distance. It's called as viscosity, and this viscosity is defined as a property which offers a resistance to the movement of one layer of the fluid over the adjacent layer of the fluid, and that another adjacent layer of the fluid is next to it. On the lower layer. Similarly, the lower layer also exerts a resistance on the upper layer. So the opposition force or the resistance force that is offered by one layer of fluid on another layer of fluid, that is called as viscosity. If it is an ideal scenario, this shear stress that is induced by the flow, the top layer causes shear stress on the adjacent lower layer, and the lower layer causes shear stress on the adjacent upper layer. So this shear stress is proportional to the velocity gradient du by dy. Okay. And if I have to remove this constant of proportionality, I introduce a term called mu. And this mu is what is called as dynamic viscosity. This is represented by the term mu, and we denote it with a term mu. Okay. So this dynamic viscosity is represented by mu. So if I have to define dynamic viscosity, it is mu is equal to tau times du by dy. So tau is the shear stress and du by dy is your velocity gradient. And this du by dy can also be called as the rate. So this du by dy is also called as the rate of shear strain, or it can also be called as the rate of shear deformation. Okay. And so your dynamic viscosity is defined as tau by du by dy. Okay. So yeah, you can define this dynamic viscosity as shear stress required to produce the one such definition that can be attributed to your dynamic viscosity. Is that clear? Okay. So what is the unit of viscosity? So if you look at U is tau divided by d. This can be represented in terms of Newton per meter squared. Du is velocity gradient. So meter per second divided by meter. So which could be cancelled. And so if I have 1 by second, it can be taken to the numerator. Into 1 by 1 per second. So that becomes Newton second per meter squared. Okay. And this dynamic viscosity is also represented by a term called poise. And this poise is nothing but 1 by 10 times of Newton second per meter squared. So one poise is going to be equal to 0.1 Newton second per meter squared. So one poise is 0.1 Newton second per meter squared. Okay. And there is also something called as centipoise. So one centipoise is 1 by 10 times of poise or 1 by 100 times of Newton second per meter squared. So it is 0.01 Newton second per meter squared. Okay. So that is a unit for your viscosity. So the SI unit, we stick on to Newton second per meter squared, but in the problem, if they give it in terms of poise and centipoise, so you should remember this definition so that you can make that conversion. Okay. We will also look at one another term called kinematic viscosity. And this kinematic viscosity is represented by the term mu. So nu is mu divided by rho, which is the ratio of dynamic represented by meter squared per second. So that is the unit for kinematic viscosity. Okay. So we will stop here. And in the next lecture, we will look at some of the problems. Thank you.